Okay, so the last time we began with the definition of the problem that we are looking at, and then we developed a little bit of machinery that is used to solve the problem. Okay, so I'm going to go over all that. I mean, I'll do a recap. So the problem we were trying to solve was called disjoint paths. This has a lot of variations, but the one we are concerned with is called disjoint paths in directed planar graphs. Okay, so the input is a planar digraph, and k tuples of vertices in the graph, and we need to find a set of k vertex disjoint paths that link Si to Ti. Okay, exactly this, not Si to maybe Si plus 2 or something. It should link Si to Ti. That's kind of what makes the problem complicated, because if you just had two sets, S and T, and you wanted to find k paths that linked S to T, k vertex disjoint paths, then if there was such k such paths, then you could find it by running a maximum flow algorithm or something. But the problem there is that these SIs might not go to the TIs if you find the vertex disjoint paths that way. Okay. Yeah. And then what we did was we went over partial orders and lattices. Okay. And then we also looked at the free group on k symbols, gk. So the free group on k symbols, in short, it is just, suppose you have k symbols g1 to gk. The free group gk is all words you can form over these k symbols and their inverses. Okay, like in a group, like as if these were generators of a group. Okay, and the free group basically consists of all words you can form from these two k symbols. But the catch is that you might have two words, g1, g2 inverse, g2, g3, and g1, g3. They represent the same element in the free group. So all words with all words with the inverses removed. Okay, you can also look at this as a kind of equivalence class. So a partition of all words over those two k elements given by an equivalence relation. But basically, it is all words that do not have a generator followed by its inverse. So the same thing that would it's exactly the same thing that would happen if you did not have any relations in. So when you give a presentation of a group, what you do is you say that G is generated by some generators G1 to Gk. Okay, you say this, and you give some relations between the generators. Okay, something like this. All right. So the free group basically is this group, whatever group you'd get with no relations. So that's the free group. Okay, and yeah. So what we'll do now is we'll consider certain functions from the edge set of a digraph to the free group, and then look at a lattice over those functions. Okay, so this is the kind of thing we'll be looking at. We'll be looking at functions. So we'll be looking at these kinds of functions, okay? And then we'll say that, yeah, we'll form a lattice on these functions. So, sorry, this is not lambda, this is A. A is the set of arcs. So the last time we had defined this partial order on the elements of Gk. Okay, so what was this? So basically, this means that okay, so it's an initial segment of x is an initial segment of y. This is what it means. Now this is a partial order on Gk. We saw that this can be extended to a lattice on Gk just by adding an extra element. It's not anything too complicated. It's not anything really. So you can always do this on any finite lattice. Because this lattice is finite, you can always do this. On any lattice actually, you can add lower bounds and upper bounds. Yeah. But, sorry? The meet and the join operation. So this partial order, this defines an infimum and a supremum, right? So it's just the infimum and the supremum. What you'd get from the partial order. So this is one word, this is another word. This is the infimum of, and these will always exist when you add this infinity. I mean, this already was there before adding the infinity because 1 is a lower bound for everything in the set. So when you add infinity, that becomes an upper bound for everything, and yeah, in most cases, infinity is the upper bound, is the join. But when this is an initial segment of this or the other way around, then one of them will be the upper bound. Yeah, one of them will be this. So that is our lattice, And now what we'll do is we'll extend this lattice to a lattice over these functions, f from v to gk. Okay. The reason we are doing this is that we'll say things like, suppose you want to solve a certain kind of problem which involves finding a function from this vertex set to gk. What you'll do is you'll begin with a very simple function, and then you'll augment it point by point, and then you'll be taking the join of functions. So certain theorems they become easier to express because of all the lattice notation. Okay, so yeah, this lattice is on gk. We can extend the gk lattice to this set, which is all functions from v to gk. Okay, so how will you extend the functions? F and g are some functions in this. F is less than or equal to g if and only if for all v in the vertex set, f of v is less than or equal to g of v. So that's how you will extend it. And again, to make this into a lattice, this is not a lattice. If you just have these functions, this will be a lattice when you add an infinite element. Okay, this infinite function takes every vertex to the infinite element here. So that is our upper bound. Okay, that will make the whole thing into a lattice. All right. So now we are going to look at a problem on these kinds of functions. Okay.
We are making GK is a free group that
Yeah.
we are extending to a function on the vertex set. Right?
Yes.
That function happens to be a lattice.
We are now looking at this set, functions from v to gk. Yeah. What I'm saying here is we can make that set into a lattice by adding this. This is our partial order on that set, and this is the upper bound. So you can make that into a lattice.
Make what into a lattice?
This set becomes a lattice. Yeah. So now we'll come to our main problem for today, which is called the Co Homology feasibility problem. Okay, and it's a problem which is NP hard in general, but what we'll look at is a polynomial time algorithm for it. Okay. Last time we looked at what did we? Co homology. Yes. So this was defined last time, and what we did was we have two functions, phi and psi, from the arc set to gk. They are called cohomologous if there is a function from the vertex set to GK such that for all arcs in the arc set, suppose this is UV, this condition holds. Okay, so if such a function exists, then these functions are said to be cohomologous. Okay. Now what we'll look at is we'll have one function and we will try to find another function that is cohomologous to it subject to certain constraints. Okay. So that is what our problem is. So the problem is called cohomology feasibility problem. So it means you're given a set of certain constraints and you want to be and a function like this, and you want to be able to find another function that is cohomologous to it, and it satisfies these constraints. So that's our problem.
Suppose there are no constraints, does that always exist a solution?
Yeah.
It is.
If there are no constraints, it is really easy. This function is
No, other than that. Non-trivial.
I mean, how do you even define non-trivial here?
Not same as the given function.
Yeah, but no, I mean, no, I don't think so. Need not exist. Yeah, the constraints will be for each arc we'll have a set of group elements. Okay, that will be our constraint. So I'll say how that is a constraint. So this is the problem we'll look at. The input is this is the set of all subsets of GK. Okay, so that is our input, and a solution to this problem would be f is this function that proves that these two are cohomologous. Okay, so this condition needs to hold, right? This is called the constraint function. So this gives you a set of elements of gk for each arc in the graph. Okay, and the constraint is this: for that arc, this which is, by the way, equal to f, equal to phi of a, this should be in gamma of a.
V to GK. F is a function, V to GK. That F is that function in the definition.
Yeah. So this is what we need to find.
It's difficult to give an example.
Yeah, I'm. It is.
Any
Pretty.
indication as to what this means? I mean, okay, we want
It is.
phi of A to be in that set. Should we put it that way?
Yeah.
Anything else other than that?
We want it to be in this set, and the way we'll use this is that we'll say that this set, I mean later we'll say, is equal to yeah, gi, okay, for some group element. It will be exactly, yeah. So this arc needs to be, so if this is the arc, it needs to be assigned the element gi. So last time I talked about configurations. So what will happen is that we'll be assigning, the way we'll be counting the configurations is we'll look at how many ways these group elements can be assigned to the arcs. Okay. So right, there is another arc B. This will also be gi. So our good configurations will be things of this sort. Okay. So this set will be exactly one element. It will be a singleton. Yeah. So that's basically what we will use. So this cohomology feasibility problem. This is much more general. We're considering a very special case, but roughly what it means is the algorithm is trying to find a kind of planar embedding of the graph, okay, and it's doing it by moving around the arcs. Okay, maybe the arcs go like this, maybe they go like this. So this cohomology, so these two paths, they are topologically equivalent, right? There is a homeomorphism that sends this to this. Okay. So that's where the cohomology part comes from, but that is much more general, I think.
This need not be just confined to planarity.
No, it is not. We do not use planarity anywhere except when going from the input to the dual to
So when you mean
this.
embedding, it's any embedding. You just
This is where we use. Up to this point, it is planar. After this, it might not be. So we use planarity to go to the dual. This problem is, yeah, we'll be looking at just problems of this kind. This does not say that the graph is planar or anything. It does not use that fact.
but it has got to do with topology, is it?
Yeah,
Trying to understand
this problem,
Yeah.
it comes from topology. Yeah. this algorithm will not use planarity at all. Okay. Yeah. So I'm going to write down what exactly we'll get today. So this is our theorem. So that's what hereditary set means, and this problem is polynomial time, and this function is hereditary. That means the set of constraints for each arc is a hereditary set in GK. In general, this is NP complete. So this problem, the most general version that I've seen is on this is a quiver, which is a generalization of a digraph, and these sets are arbitrary, okay, not hereditary. So when these graphs are digraphs and digraphs, not planar digraphs, just digraphs, and this set, uh, these sets are hereditary, this problem is polynomial time solvable. That's the theorem, and that's what we'll look at. Okay. This will be later used to solve the, I mean, this will be roughly what we'll use this for is to kind of see if two configurations are equivalent. Okay, configurations in quotes.
Segment, you mean substrings, right?
Substrings, but contiguous substrings. Not, yeah.
Not subsequent substrings.
Yeah. So this is the algorithm. What it will do is, this is a rough outline. So roughly we'll define a function for each arc in the graph. Then we'll, unless the problem does not have a solution, we'll be able to perform this step. And then in the end, we will not actually take the join of all the functions, but some of the functions, and that will give us our solution, if the solution exists. Okay. Why it is not? Yeah. No. This is that having subsets is better. This is saying that for all hereditary sets, this solves in polynomial time. Okay. What we are going to use is just going to be singleton sets, but this is the theorem that if the sets are hereditary, we can solve the problem in polynomial time. Okay. Okay. So the way this will work is, all right, wait. So what kind of a solution do we need to find for this problem? The solution is like over here. It's another function from the arc set from the arc set to the free group, but this condition can be expressed in a different way. This condition can be expressed as you need to find this function f. Okay. So when I defined cohomology, I said it was an equivalence relation. Okay. So that means it is. I mean, it is not hard to check even. It's an equivalence relation, so it is reflexive, right? So this what we need here is to find this psi function, which is cohomologous to phi. So f of u inverse times psi of a, f of v equals, right? This is what we need to find. But there's no constraint on this psi, right? Okay. We can find any psi such that it satisfies this condition. Okay. And the way we can do that is this. If you cancel out the terms, you can write it as some g inverse of u times g of v, where g of right, we can write it as that. The condition from the cohomology, I mean, the cohomology condition is just that.
The solution to the problem is to find all this. The definition is fine, but
Yeah.
then the property depends only on phi, which we already know. I mean, we can check that for every a, phi of a is in gamma of a or not.
Yeah.
Then the problem reduces to just finding a homologous function to phi.
Wait. You're saying phi of a should be in gamma.
Sorry?
You're saying phi of a should be in gamma. No.
Phi is the initial function.
No. Actually, the condition will be that this should be in gamma.
Okay. That says that phi of a is in gamma, right? inverse of this, that thing is nothing but phi of A. No?
Yeah.
Then it is not a property of the solution, it's a property of the input.
Wait, what did I write? Okay, yeah. This has to be equal to phi of A, right?
I agree that says only
You have
all
to,
of this, right?
yeah.
Then why do we have to, I don't understand.
Yeah. I think yeah, that's what I'm thinking. It should be, but no. I mean, if it's not, then it just no. I think it is phi of A. Yeah.
1 minute.
Wait, is it correct?
Gamma of A. Just
Huh?
change that to psi of A belongs to gamma of A. Is psi of A equal to F
Yeah.
phi of
Psi of A should be in gamma of A, and this
should be equal to psi of
this should I mean this might or might not be in gamma of A, but these functions, this function should push it into gamma of A. So it
is this equal to the
Uh,
is equal to psi of A? No,
Yeah,
is
yeah.
both directions true? The definition says that phi of A is equal to this into psi of blah blah blah. But now, I mean, is the inverse very easy to see?
No, wait.
No, for me, I have to write it out. Definition says phi of A is equal to F inverse psi of A F of A. We are interchanging phi and psi. That we can do only if they are invertible. I mean, invertible in this sense. I'm asking, does it follow? It doesn't follow from the definition, straight away at least. You have to do some work to say that it follows.
Yeah, that's how it's actually given. So it has to be this function has to be cohomologous to phi, and for each arc it has to belong in that set. This is the correct.
This has to belong. This necessarily need not be phi of A.
No, this is psi of A. Psi of A. No. You need to find a function psi of A such that, so the way it's given in the paper is that this should be in gamma of A.
Psi of A
Should be in gamma of A.
Okay. Is it
Okay.
true that psi of A is always equal to this?
Yeah. So when I say that via F, psi is cohomologous to phi, I mean this condition holds. Psi of
Definition says phi of A is equal to F inverse of U psi of A F V. We are interchanging phi.
Yeah. Okay, that's this part. So what you can do is, so this F is actually inverse of something. Yeah. So so the way I wrote the definition was that this was it, right? No factors on either side. F inverse of U psi of A F of V, right? So you can do this. You can take the inverse and you'll get that. These are equivalent, right?
No, I'm not able to see it straight away, but
no, it is not, because if you replace, I mean, if you make this substitution, what this becomes is G of W, and what this becomes is G inverse of V. So
G is inverse.
yeah, so the relation is an equivalence relation, so it's symmetric. This is what it's. Yeah. No. In this problem, we are asking for a function that is cohomologous to this function that you are given, and it satisfies this condition. For each arc, it should. So maybe it's better if I write just.
You just write psi of A belongs to
Yeah,
gamma of
psi of A. Yeah, that is how it is given in the paper. Okay. Gamma of A. So this is the problem. So, huh? Psi of A is no. The definition is that the definition of cohomology is that psi will be cohomologous to phi if a function f exists. Okay, this is. But what this is saying is that you need to find that function, and that function has to satisfy these constraints. Okay, so the definition was this. If this is satisfied,
but this means phi is cohomologous to psi.
Yeah.
But you want.
We want a phi cohomologous to psi with some additional constraints on psi.
Like, is it a
Yeah, it is an equivalence relation. It is. Yeah, it is. It is an equivalence relation. So that is what we need to find. Okay. And what I was doing over here is that I was trying to show that finding this is equivalent to finding an f. Okay, because what do we need to show? We need to show that there is an f such that right, and it's an equivalence relation, it's symmetric, so there is a G so basically what we need is to find this G.
Don't erase if you don't mind.
Okay, no, I'm erasing because I'm trying to say that this.
I understand, but
Okay, yeah, this is, yeah. Okay, psi of A must be in gamma of A, and the whole thing is equivalent to finding this function G such that when you do this for every arc, the product is in this set. Okay, so it is equivalent to find okay, it is equivalent to finding this function. So that's sorry about the mess. I was trying to get to this. So yeah, now we'll see how to get this function.
It's not
Right.
that. Fu phi of a f inverse of b.
Fu. No, I mean, yeah, it is that, but I mean, if you take f to be f inverse.
I thought, but then the domain case. So it's
No, no.
no. That I understand. I'm just
Yeah.
asking if it's fu.
I mean, I'm saying this is G. This is different from that. Yeah.
Because GU, no?
This follows. Okay. I mean, if you just write it down, it follows. Basically, because the relation is symmetric. That's why it is this. Okay.
What's the difference between SF and
No difference. This is for, yeah, I just wrote that to have two different names for the same function. So now we'll try to find this function, and the way we'll do it is, for each arc we'll define a function fa. Okay, and then we will take then we'll find a function that is larger than it for each arc, and for all these functions we'll take the join. That will give us a feasible function. Okay. So, okay, sorry. This equivalence, is it clear? We need to find an f. Okay. And if such an f exists, this f is from this set, right? Gk to the a, right? This is a function from, sorry, not, it's a function from the vertex set to Gk. All right, and these functions have a name. So if this problem has a solution, then we will say that if then f is called a feasible function. Okay, and what does this mean? This means f satisfies that condition. Okay, so feasible just means now I'm coming away from the problem to just these functions. Okay, so now you can forget about the problem. F is called feasible. You have fixed some phi before. F is called feasible if this condition holds. Okay. So this might not hold, right? If you take any for an arbitrary function in that set, Okay, I mean that is pretty easy to see, right? Why should the function be satisfy that condition? So maybe we relax that condition a little and we can get somewhere. Okay, so to relax that condition, we go to what are called pre-feasible functions. Okay, so this phi is fixed, gamma is fixed, and now we are looking at all functions in this set, right? So pre-feasibility. Okay. This function is called pre-feasible if whenever this condition fails, it is of a certain kind. Okay, if f inverse of for whenever the feasibility condition fails, the value of this function is 1. Okay, that is what is meant by pre-feasibility. Okay, so
Correspond to a co-homology.
yeah,
Satisfy this part. That should lead to a homology cipher. Is that true?
yes,
It has to.
yes. That is, I mean, from now on, the cohomology condition holds, and
Oh, there's just additional conditions.
yeah. So we have, for now, we are fixing phi and gamma. Okay, so we have feasible functions and a generalization of them, pre-feasible functions, and we will look at how they behave in the lattice that we defined earlier. Okay, so now I'm just going to write down a bunch of theorems. We'll not look at the proof; they are very technical. Basically, they are about how these pre-feasible functions behave in the lattice. Okay. So this is our lattice of functions. Okay, that is our lattice. Now, this is a lattice, but suppose you had two functions in this lattice, f1 and f2. We don't know if they are feasible or pre-feasible or whatever. Will this be feasible? Not necessarily, right? Now, when I say feasible and pre-feasible, I have fixed phi and gamma. Okay.
Phi and gamma.
Yeah.
Of course, good.
Yeah. So these functions, I mean, first of all, they might not even satisfy the cohomology condition. Okay. But if they do, are they necessarily feasible? No. I mean, phi could be cohomologous to a function's psi, but maybe not relative to these constraints. Okay. So we are deep into this now, 2 levels at least. So we have fixed phi and we have fixed gamma. Okay. And now I'm talking about these functions, which are from
If gamma
this
is
set.
not fixed, there is no guarantee that that holds, even though they are feasible. But if
Yeah.
you fix gamma, maybe there is something out there that is going
Yeah.
to
Yeah. Or yeah. No. What I'm saying is, this could have been just GK, right? Then finding a cohomologous function is really easy. I mean, you could output the same function. That's a solution, trivial, but it's a solution. Okay, so relative to this and this might not be feasible, the F1 and F2, when F1 and F2 are arbitrary. But we can say something about free feasibility. If these two are free feasible, this is free feasible. Okay, so
Pre-feasibility implies feasibility?
no,
Not.
free feasibility does not imply feasibility.
That is not revealing to. Whereas if there exists an A for which that does not hold, it means it's not feasible.
Yeah.
Okay. But feasibility implies pre-feasibility. So if F1 and F2 are
Feasibility, they are pre-feasible. This is a generalization of feasibility. Yeah. So this is you can show this. This is in the paper. F1 if both functions are pre-feasible, then their meet is pre-feasible. Okay, so this is yeah, it will basically follow from, so what does it, so I'm trying to give a rough idea of what is going on here. So F1, F2, you have this, all right, and you want to find you want to find this function. They are both pre-feasible, and you want to find this function. So this function, this is less than or equal to F1 and F2, right? That means this function is an initial segment of this and an initial segment of this on every, suppose this is G. So this is an initial segment of this and this, and if you look at this condition, does not belong to gamma of A. This thing is an initial segment of F1. There is a lemma before which will allow you to say that basically it will allow you to say that these f1 and f2, they are the condition for f1 and f2. If you look at this, all right, this will be a segment of this. The other thing will also be a segment of this, and they do not belong to this, and then that means that they are one, and it's. I'm saying the initial segment thing is what will be important. Okay. So this theorem, what does it give us? It gives us, first of all, that this is finite, right? This is finite. Okay. So okay, this is finite. Let f be any function okay. F is any function. If you look at this set for that function, all functions larger than it in the lattice which are free feasible. So this theorem will give us this is what it will give us. This is not the important bit, this is the important bit. You keep taking the meat of all the functions one by one, and the functions you'll get will be free feasible. You take the meat of what you get with other functions over here, and eventually you'll get the meat of the whole set. Okay. So what I'm trying to say is that this exists and is pre-feasible. Okay. And it exists anyway because it's a lattice, but the pre-feasibility is the important thing here. So okay, it exists. It exists. It always exists. But there's a catch here, which is that this set might be empty. There might not be a function larger than it that is free feasible. Okay. In that case, what is the infimum? Infinity. Infinity. So now we will look at, so from f you take this function which is this set. So this is defined for every function in GK. For this is the infimum of this set, which is the set of all pre-feasible functions that are greater than f. So f bar, in words, it is the smallest pre-feasible functions that is greater than or equal to f. Yeah. So
As infimum of S is the smallest
Yeah.
feasible function, not smaller than.
yeah. This is not exactly correct, because if it is infinite, then it's not. But if it is finite, then
If
this.
it's not empty, then this is.
Yeah. Yeah. Okay. All right. So this is how you define these functions. What does it mean? There are these arcs going out of U. This is A, maybe this is B. Fa would be, Fa of U would be phi of A, and maybe there is another arc that goes from W to Z. Fa of maybe this is C. This will be 1. So phi of A for U and 1 for everything else. That is our function. Okay. Right. Okay. So now we can get into the algorithm. There is a part which involves the two major steps are okay, finding this from F, and then X is a set that we need to find. What I'm saying here is this X will need to satisfy some conditions, two conditions.
Okay, X is subset of the vertex set.
Yeah. It's a subset of the arc set.
Okay, then X square is what?
X square is arcs and arcs.
Correct, but then
Yeah, there will be a square later. So such that this happens and a second condition holds, which is that okay. So these are the two parts of the algorithm. This is the complicated part. This can we don't have time for it today, but this is where the poly in A plus sigma plus k time comes from, okay, and this is something easy. So how is it easy? This is an instance of
A inverse is what? A is an arc. It's
the opposite arc. Yeah. It is an instance of 2 sat, so it can be solved in polynomial time. So how is it an instance of 2 sat? Okay.
It's you mean it either has this or that.
Yeah, either A or A inverse will be. So what you can do is
FA that we defined here is finding FA bar is easy.
no, it is not. We'll use this algorithm.
We use that.
Yeah.
So even for the special FA, it's still not.
Yeah, it is. This so H you can figure out in polynomial time, right? You just need to go through all the arcs and check for which ones this happens, and you'll be able to find the set H. Find H, and this for each for each arc you construct this function first and then apply this algorithm to find this, and that algorithm will tell you that okay, this is finite or it does not, or infinite. Okay, so again this set, I'll call this R squared. Okay, R is also okay. Find so both of these steps are polynomial time.
The same poly, is it?
Uh,
How many factors will be used? The A, sigma.
the three factors are coming in here.
Only
Okay.
because of finding FA bar.
Yeah.
But if you just use that as a black box, what is the maybe A you will need?
So A will be roughly n squared, and n squared times this polynomial. Right.
K and sigma will not be enough.
Yeah. No, it will, because to run this algorithm, you need to run this algorithm, you'll need this much running time. So what will happen is that the way this algorithm will work is that this phi function, where it can be, so phi of A might be G1, G2, G3, and so on, right? Any combination. So the algorithm, the algorithm, what it will do is it will change the graph and split this phi A into phi A1, A2, A3 such that each of them is one symbol. Okay, that is why this sigma comes in, and the K will. Where does the K come in? Yeah, the K is also. So to perform this step, you'll need this much time, and this whole thing will take time n squared times whatever this polynomial is. Yeah. So you find these two sets, and then you construct a you construct a 2CNF. So what will that be? And so H. This is actually something else. This set. It's not this. Okay. Yeah. I thought the conditions were the same. No. So this set is A and A prime, all sets A and A prime such that 5 minutes. Okay. So
It's prime, not inverse. A prime. A prime.
yeah, it's A prime. So all arcs A and A prime such that when you take their join, take the join of their bars, what you get is, yeah, something finite and pre-feasible also. Okay. Yeah. So this you can check, right? How will you check that? So
What is the complexity of finding join in general?
join, so join will be either one of these functions or it will be infinity. So is that true?
Not in general at least, but for maybe.
No, not. I mean, the pointwise join.
Pointwise.
You take the pointwise join and that will work. Yeah, if you define this pointwise join will work, right?
For the special FA.
For any f, the pointwise join will work.
Okay, so you're saying the pointwise join is either infinity or one of the two. Is that true?
No. What I said, that was wrong. But the join here is the pointwise join.
No, that isn't.
Yeah.
How do you find the pointwise join?
The pointwise join will be, first you find these functions and then go over all vertices. So that will be like order n times, so you need to find these two functions. So that will be twice polynomial in this
True, so
times n.
using, finding any join is easy, is it?
Yeah, the join is the pointwise join.
No, correct. Finding pointwise join for one point is easy.
Oh, that is just the join in the group, right? And in the group, that is
Okay, what is the complexity of finding join in the group?
in the group. Yeah, okay. What I said is correct for the group. Okay, so x join y is y if x is less than y, or the other way, or
Group at least.
yeah,
That is
yeah,
the initial segment part. And
yeah,
so.
yeah, or it is infinity.
Or it's infinity.
Yeah. Now, if you take the pointwise join, you'll get that. So you figure out the join, and then what you do is yeah. So how will you encode this condition? this is R as before, okay, but earlier I was squaring it, now it's just R. So for all AA prime in R complement, not of, so that basically means these two should not exist together. So right, and this is an OR, if you does not belong to X or this. Yeah. So you can write the whole thing as a 2CNF, and this that is just a set variable. So this you can write as for each. This will mean XA is 1. So a 2CNF formula on about n squared variables that you can solve it in time polynomial in n. Yeah. So all in all, you can solve this whole thing in polynomial time if this you can do in this much time. Okay. And this is where you use the fact that gamma is hereditary. Okay. So maybe we will look at this next time, or maybe we'll move on to how to apply this algorithm on an input graph.